everybody! Today we're going to talk about graphing linear functions. This goes with the learning goal. I can represent functions with equations and tables and create graphs from equations and tables. And really this is again a continuation of what we've been doing, but we're going to talk about two different kinds of data that we might be graphing within our linear functions and then just extend our knowledge a little bit more. So when you're graphing actual real world data, there's two different kinds of data that we might be graphing. We might graph discrete data, which is data that involves when counting something. So if I'm graphing the number of people or something like that, that's discrete because I would just count the different units, count the number of people. And when we graph discrete data, then it doesn't make sense to be talking about half a person or 3/4 of a person. And so we represent the fact that we're graphing discrete data by using a dashed line instead of a solid line. When we graph continuous data, that's data where the number between any two of the data values do have meaning. So for example, if I'm measuring height, or I'm measuring the amount of time it takes to do something. Those are all measurements where the data is continuous. You can always break it down further and further, and those smaller breakdowns have meaning. And so for that, we graph our lines using a solid line. Here's an example where I am graphing some discrete data. We have the function c equals 15t, which represents the cost in dollars of T adult tickets to a museum.
A museum? Is that a museum of explosions?
And we want to make a table and graph that function. So there are two steps that we want to follow when we're trying to graph data and we're not sure if it's discrete or continuous. The first step that we want to follow is to determine whether we are dealing with discrete data or continuous data. And just ask yourself, does 1.5 or 3/4 make sense in this situation? If I'm talking about the number of tickets, I cannot go up to a ticket counter and say I'd like to buy half of a ticket. And so in this case, we're talking about discrete data. Then I'm going to follow my same steps that I did before to graph this function. So those steps are to make a table, graph the points, and then connect them with either a dashed line if I decided that my data was discrete, or a solid line if I decided that my data was continuous. So in this case, we decided our data was discrete. So I've made a table over here, and I'm going to figure out the cost for these different numbers of tickets, and then I can put my graph in. Okay, so next to my table, I can just write the different functions with the different values for t substituted in. If I had 0 tickets, I'm going to be doing 15 times 0. And that's going to be 0. And I'll just write the rest of these in. So this I can see would be $15. If I buy 3 tickets, that's going to be $45. And if I buy 5 tickets, that's going to be $75. So now you can see that I can put these 4 points onto my graph. I have 0, 0. I have 115, 345, and 575. I know that I want to graph this with a dashed line, and that represents the fact that I have graphed discrete data, and so only whole number amounts would make sense for the number of tickets. Okay, so now we're going to extend our knowledge of linear equations a little bit more, linear functions. If I graph my line, so on this last one, the y-intercept is a point where the line crosses the y-axis. So right here, I can see that this line is crossing the y-axis at 0, 0. And so I would say my y-intercept is 0. I just named the point where my line crosses the y-axis. I don't name the x part of that, just the value on the y-axis where it crosses. So that's the point where the graph crosses the y-axis, and I just name it with one value, whatever the value on the y-axis is where it's crossing. The x value is always 0 because we're crossing the y-axis. The slope-intercept form is where you have an equation like this one here, y equals 3x plus 4, and it has to be arranged exactly like that. So it has to say y equals some number times x plus or minus some other number. You could be subtracting because that's the same as adding a negative. But you have to have some number being multiplied by x and then adding a second number. When we do that, when we arrange an equation into that form, this first number right here that's being multiplied by x ends up being the slope of the line, and the second number here ends up being the y-intercept. And usually when you see people talking about slope-intercept form, and this is very commonly used in many levels of math, the way people write this in general is they write it as y equals mx plus b, where x and y are the variables in the equation, and then m is going to be your slope, the number that represents the slope, and b is going to be your y-intercept. And these will both be numbers in your equation. They will not be variables, they will be numbers. So that's called slope-intercept form. Anytime you have an equation for a line that has a y and an x in it, you can rearrange that equation into this form. You have to solve for y. But for the most part, what we're going to be dealing with, the equations will already be in this form, and so you won't have to manipulate them yourself. The last thing here is a linear function, and we've already talked about linear equations. This is just another way of naming that. A linear function is a function where all the points that are solutions to that function fall on a straight line. So here I have an equation, and I can see that this is in slope-intercept form, but I can ignore the fact that this is written in slope-intercept form, and I can just graph it the way that I normally would by creating a table, putting in points, and then graphing those points on my coordinate plane. So I'm going to go ahead and put in some points now. So you can see when I graph these 5 points, they all fall on a line. And then I can go ahead and I can draw a line through those points, and I would want to put arrows on the end of my line showing that it goes on and on forever in both directions. And this is not a discrete equation because there's no real world situation to tell me that the numbers in between my whole numbers don't make sense, and so I'm graphing this as a continuous line. The answer to the free response question is mushroom pajamas. Now I could take that same equation and use the fact that it's written in slope-intercept form to graph my equation and not have to make a table. So remember, because it's in the form y equals mx plus b, that tells me this is slope-intercept form. And I know that this first number right here is going to represent the slope of the line, and this second number right here is going to represent the y-intercept. So remember, we said the y-intercept is the point where my line crosses the y-axis. So I'm going to draw a point here at 1 on the y-axis. When we have slope, as Yoder talked about in the last video, that's the same as the rise over the run. In other words, rise, meaning how far do I go up and down, over how far am I running, how far am I going horizontally. So that tells me that from this point right here, my y-intercept, I need to go up 3 because my rise is 3, and I need to go 5 to the right. So I'm going to go 1, 2, 3, 4, 5, and put a point right there. And so now, just based on those 2 points, I have graphed this line. So now I can just draw a line through those 2 points and put arrows on the end, and I have graphed my line. So there's 2 ways I can graph a line that's written in slope-intercept form. So here are your free response and multiple choice questions. Go ahead and pause the video and answer those now.